wide variety of different structures, and properties of each of them is different from others. So this is so-called chirality issue. In every single nanotube, almost in all of them, band gap is different, electronic structure is different. So you cannot make standard device using carbon nanotube. But you don't have this issue with atomic graphene because it's a flat layer of graphene. And talking about anisotropic effects, there is always a conducting, so-called metallic direction in this layer. And this is the direction of current propagation through the atomic graphene. So for my experiments, I was using Zyvex nanomanipulator. This is truly unique tool, which is a 4-probe stage with probes connected to piezo elements. And using this tool, you can really move tiny little things, which are like a few nanometers in size. But this is, of course, in Zyvex commercial. Normally, you can move things few microns in size. But this is one example of nanofabrication. This is basically surface of HOPG, which is highly oriented graphite. Sorry. So it's a bulk material, but you definitely can distinguish atomic layers inside the electron microscope. This is the probe attached to the nanomanipulator. So experiments, one of the experiments I tried recently, I just attached a sharp STM probe to the piece of HOPG, highly oriented graphene, and apply voltage to it. Apply voltage between HOPG and probe. In this case, top layer of this graphene will stick to the probe electrostatically. This is electrostatic attraction. And then we have two options. First option, just to measure electrical properties between these two probes. This is totally suspended atomic layer. So imagine this is just layer 1 atom in thickness. And you can measure properties of this layer, just completely suspended. There is no contribution from substrate in this case, because substrate is another issue. Sometimes people say that substrate significantly changes electrical properties in conductivity. Or another option would be just to drop it on the substrate. See, and that's what I did. I just attach it to the substrate and then change the polarity on the probe. And this is this layer of graphene on the substrate at the location where I want to put it. These are marks for electron beam lithography. After that, you can fabricate the device lithographically. And here is, let's say, double layer, 2 atomic layers of graphene between the trenches. I was trying to perform this mechanical measurements using our nanoneedle and graphene monolayer. Unfortunately, it didn't work out because graphene is so strong. It has like Young's modulus thousands of gigapascals. It was practically impossible to deform it. I broke a few needles, but nothing worked out. Okay, but that's good. I mean, I was surprised that it's so strong, such a strong material. Okay, this is a typical measurement. This is the graphene layer between 2 metallic probes. This is monolayer in this particular case. Now this is the IV curve for this monolayer. You see small effect of Schottky barrier because graphene is not completely a metal. It's a semi-metal, or very bad metal, let's say. But the good thing about this metal, well, it's not a metal, it has metallic properties, but with modulated band gap. So this is the only material which has metallic properties, but modulated band gap. So you can make transistor on the basis of material with metallic properties. And this is what is so good and great about graphene. This is why people are so attracted to this material. Okay, so this is an IV curve for monolayer. For a group of layers, this is already like 4 or 5 layers of graphene between the electrodes. And we put a little gallium on the tips to improve contacts. Conductivity is sufficiently higher. Well, the reason for this is obvious, more or less, because now we have propagation through bulk, not just through one atomic layer. And in this case, we obviously expect increase in conductivity. Well, this is also a very interesting experiment. This is an example of anisotropic properties of graphene. Let's say if we measure conductivity along the layer, you will get, well, this is what I call parallel. You will get pretty high conductivity. But if you measure across the layers, across the two layers, you will see significant drop of conductivity. What happens actually along the layer, electronic scattering is much smaller than across the layers. Electronic scattering between the layers of graphene is much more significant, and that's why we see this effect. But again, it's just preliminary results and very simple explanations at this point. Obviously, we need a lot of theoretical modeling and work of theoreticians on this subject. And this is another experiment, pretty cool one. I like it a lot. So we have 3 probes. It's really hard to target a small piece of graphene like 10 microns with 3 probes at one point. So this is not monolayer, it's like 7 layers probably. So we attach electrodes, and it's suspended between the trenches. We attach electrodes to it, and then push it with a 3rd electrode in the middle. So what we see in this case, the stronger we push, the higher the pressure, the higher the conductivity. And the reason for that is, from my point of view, again, you have electronic scattering between the layers, but then you squeeze them together, and your current will flow not through the top layer, but through the bulk material already, because it will be strong interaction. Scattering will be much smaller because of this compression. And that's what you see, rise of conductivity. And this is something we cannot understand at this point. This is dependence of conductivity from the length of graphene layer. So for graphene, you cannot apply regular laws of let's say, electricity. It's not like current. Voltage equals current multiplied by resistance. It's different example. It's ballistic transport. So what we found out that if we decrease the distance between the electrodes, we will see increase in conductivity. The shorter the distance between the electrons on the graphene layer, you will see a significant increase in conductivity. But again, to explain this, we need more work of theoreticians, and on this matter we collaborate with famous theoretician Dr. Wu. He works in Louisville Physics Department. And these are the conclusions. I'm not going to read them. It's just, the point of this talk is just to introduce you physics of nanostructures, what nanostructures are, what is self-assembly, and what are the possible applications. Talking about future prospects, I believe that in my future work I will expand my knowledge about gold nanoparticles and go deeper into fabrication of fuel cells and gas sensors. I'm planning to work on both of them at the same time. And also, I'm really interested in the properties of atomic graphene and graphene-based polymer compounds. Thank you very much.
Questions for the speaker?
I have a question about the nanoneedles.
Mm-hmm.
And you're making them by taking your silver-coated needle and dipping it in gallium.
Mm-hmm.
Do you have any idea what the composition of your alloy is?
Yes.
I mean, I'm a chemist, so I'm
Yes.